Today, however, we're going to talk about the mathematical underpinnings of quantum mechanics that are developed more or less by two people. And they go about it by different approaches, and they get the same answers, totally compatible with each other, totally the same, identically the same. They go about it by two different methods, one of which is totally unfamiliar to the physics community, and the other is quite a bit closer to what the physics community understands, and it's the one that most of us use most of the time. In addition, today we're going to discuss why it is that statistics or probability comes into physics in a really strong way, and our discussion of things being statistical or statistically governed, like the lifetime of an atom in a certain state having statistical properties, was premature in a sense, because it comes from this. It turns out all that we can understand about a quantum mechanical event is the probability that it happened. Everything else is just guesswork. Okay, now that means we're going to talk about the formulations of Heisenberg and Schrödinger. Each one will, of course, win their Nobel Prizes. They will each give you a way to interpret quantum phenomena. And what is the meaning of what they do? Very important. What does it mean when we have two different formulations and come down to what does it mean when we get the answer by each one's approach? And if both of them happened in 1925. Prior to 1925, it's a hodgepodge. It's a mess. You have hypotheses, principles, theorems, and recipes, and it's not a logically consistent theory. However, I want you to think about this, and maybe even we can take a couple of minutes to discuss it. These guys are going to do and formulate the mathematics of quantum mechanics. What would that mean without the concept of quantum mechanics? What would it mean? Would they even have done it without the work that had gone on before? Is their mathematics and their approach to giving you the way of calculating things of any use without the concepts that were developed earlier on by people like Bohr, by de Broglie, by Pauli, by the other people who put these ideas in place, that now these people are going to give you the mathematical hard underpinnings. So what I'm getting at is, we come to 1925 and we finally begin to see a hard mathematical underpinning to quantum mechanics showing up. But without the idea, the concept of quantum mechanics, starting with Bohr, it doesn't quite make any sense. You don't have a reason to do this. So it's all built on what Bohr did way back in whatever year that was, I can't remember. So here we are in 1925 with a mess of stuff, a very neat philosophical structure starting with Bohr, but no logically consistent theory. And these two guys are going to formulate it using two different approaches. Prior to 1925, every quantum mechanical problem, every theory that was put forward, every quantum theory problem had to first be solved in terms of classical principles. Each one of them, you had to find out what you wanted to get using your quantum correspondence principle, and then you go and translate all that classical stuff into the language of quantum physics, and you describe classical things like position, momentum, and so on, and you converted it into quantum physics analogs. Now, nowadays, you don't even bother to do that, do you? You don't figure out the position and momentum electrons whizzing around atoms. It doesn't make any sense anymore. Okay, but that's what you had to do back in the day before people really understood what was going on. So, in 1925, correspondence had enabled you to retain these classical ideas, energy, momentum, angular momentum, spin, and so on. As we discussed, spin was all that was left when these guys came up with the idea of spin, Gauss-Schmidt, Newton, and Uhlenbeck. And then you had to tailor the results to fit the experimental data. You had to adjust things and make the parameters fit so you could come up with an answer. And Heisenberg finally recognized that there was an alternative to this rather cumbersome approach, and he published it in a paper with this rather long title, On a Quantum Theoretical Interpretation of Kinematical and Mechanical Relations. Okay, would you ever pick up a paper with a title like that and read it? You wouldn't. It was published in German. Translated. Within months of this paper, Schrödinger publishes his paper with the now famous wave equation for quantum mechanics. So these two are essentially published at the same time. And actually, Schrödinger's is not a wave equation. It's a complex diffusion equation, which means that this famous little equation that you can speak of anytime you wake up at night is a diffusion equation. You notice that's a partial with respect to time, not a partial squared with respect to time squared, so it's not a wave equation, it's a diffusion equation, and this is the Hamiltonian operator, and psi is a wave function, but it's a complex wave function. Okay? And that has to be interpreted, and that's going to be one of the crucial steps made in this aspect of quantum mechanics, is how do you know what that wave function means? Okay, so here's back to Heisenberg's paper, and he says to formulate a proper quantum theory, you must abandon the classical description of motion and instead describe nature by an analysis of observable magnitudes. Now that's a philosophical statement on Heisenberg's part, that all that matters are the observables, everything else is meaningless. Who cares what some other things are? All it cares is what I can measure. And these observables are optical frequencies and intensities. In his paper, he actually calls them dipole amplitudes, but it turns out that's what he's talking about. Frequencies and intensities. And he struggles using what he calls an unusual multiplication to present a formulation of quantum phenomena. And today we understand this unusual multiplication as matrix approach. We're going to talk about why he didn't know anything about matrix approach. In a few moments, you will find out that it's because matrix mathematics had only just been invented. Sometimes things happen in support that the mathematicians were just inventing matrix mathematics. And the first book was published in English in well, we'll see in a few moments. It was published when Heisenberg was just 6 years old, so you can't blame him for not knowing. Anyway, a little bit about Heisenberg, the person. Now, I don't know if you can see this that well, so let me turn this off for a moment. That's Heisenberg over there, Werner Heisenberg. This is his older brother, and that rather stern-looking gentleman with the Prussian helmet on is his father. So you can imagine that Werner is going to be influenced by things very Germanic in his upbringing, and he's going to have some very stern sense about him about things related to Germany and German culture, which is described by this last line. He's born in 1901, so he's 24 years old when he revolutionizes quantum mechanics. In World War I, he left school for farm work as his contribution to the war effort. Well, World War I starts in 1914. He's only 13 years old when he steps out of school and goes to work on a farm. maybe he's 15, not immediately. But anyway, you have to understand that this is very important to Germany. The Allies had blockaded Germany's ports. They had prevented not only war material from going into Germany, but food. And Germany was hard-pressed to supply food to its very large army and to its civilian population. So work on a farm was very important for the German war effort. So Heisenberg was doing his bit. And he goes back to school at the end of the war in 1918, and goes on and gets his degree, and we'll see where he was at age 24 when he revolutionizes quantum mechanics. The elements that form his personal values are rather interesting. He rebels against what he calls non-ideal values: capitalism, materialism, hypocrisy, and moral decadence. The 1920s were a time when people throughout at least most of the world were behaving in ways that seemed to be morally decadent. It was after the Victorian and Edwardian eras. Women were wearing short skirts. There was a lot of drinking and smoking, and jazz music was coming about, and there was what appeared to be moral decadence amongst the people. And Heisenberg felt very strongly against that was a terrible thing. Maybe. Capitalism was running rampant, and that meant that poorer people were getting poorer and richer people were getting richer, and he felt there was no need for that extremity. And materialism, well, you know what that is. And he was a member of what is sort of a closed circle of like-minded friends, people who felt the same way he did about these issues. And it was referred to in biographies of Heisenberg as a group which had a harmony of souls, meaning they thought and felt similarly. And he did have a love of nature, spent a lot of time hiking, skiing, being out of doors, and so on. So this final bit here, a deeply felt affinity with German culture, is a rather important part of his character. Now, a little more history. He graduated with his PhD in 1923. You understand there's a gap there because of the war and his not going to school. And Sommerfeld says of him, "It may be that you know something, and it may be that you know nothing. We shall see." Okay, this is his advisor speaking. But at his thesis defense, he's unable to answer an experimentalist, Wilhelm Wien's, question about the resolving power of optical instruments, something any one of you could do at any hour of the night, and how a storage battery works. And Wien only lets him pass after Sommerfeld, after telling him this, strongly and vigorously defends his pupil. So now that tells you to pick your advisor very carefully. In 1925, he actually is working, he goes from his PhD, he goes to work with Max Born at Göttingen, and there he and Pauli attend Bohr's lectures. And they both wind up going to Copenhagen to become Bohr's assistant. Remember, we talked last time about, while Pauli was there, he didn't want to work on what turns out to be Heisenberg's matrix stuff. Oops, went the wrong way. He does some other things. Pauli comes up with the exclusion principle and eventually interprets the periodic table and gets his Nobel Prize. But before we go on any further, it's very important to sort out a problem that Heisenberg faces in his life, and that is his life and work under the Nazis. In 1932, the same year that the Nazis come to power in Germany, Heisenberg won the Nobel Prize for his 1925 work, the paper that shows this way of analyzing quantum mechanical problems. And I have to emphasize that no one claims that Heisenberg was in fact a Nazi. He never joined the party. He doesn't carry a card, but he did participate in the Nazi scientific community during this period, 32 to 45. There were German scientists, pretty well-known ones, who were Nazis. Johannes Stark, Ernst Pasquale Jordan, we'll talk about him in a moment, and Philip Lenard, just to mention a couple. There were others as well. Heisenberg stayed in Germany. He did not leave, as did other prominent German scientists. In fact, people contacted him to come out and leave the Nazis. He wouldn't, because he felt so strongly about the German culture. He worked in the Nazi scientific establishment, rising to become, and we call it the Oppenheimer of the Nazi Atomic Bomb Project. Oppenheimer was the leader of the American and the Allied bomb project, so Heisenberg is in fact the Oppenheimer of the Allied bomb project. And tomorrow night we're going to see the play Copenhagen and try to understand his 1941 visit to Niels Bohr in Copenhagen and try to understand what it is he tries to say to Bohr, and maybe even what it is that Bohr tries to say to Heisenberg, because it's a meeting that's fraught with ambiguity. And what would you have had them say to each other? Or what would you have had them not say to each other? So, yeah.
Actually, I don't recall anymore, but I remember back in my quantum classes, one of our professors told us that I think it was Heisenberg, he had in Switzerland as well, and there was an agent, I don't know, from America or Great Britain, that actually was there to somehow see what he's up to, if they wanted to take him out or not. And after this, they just, this guy didn't understand anything, and they said, okay, it cannot be used for anything, so they let him live. I don't know if it's actually true, but that's one of them. I think it was related to this dude. Would make sense.
Yeah, you'll see in a few moments some of the things that did happen.
Okay.
I'm going to go through it because this whole business of Heisenberg's work under the Nazis is part of the story of Heisenberg and part of the effect of society on science and how it affected things. What happened, of course, is some people found out what this project was doing during the war, and they decided it was going in the wrong direction and let it go that way. It was wasting resources. Okay, so let them waste resources. It was fine with us. But the point is, it could have been going in the right direction, and as it turned out, by 1945, they were going in the right direction. That's what was very scary. It happened to be too late for them, for the Nazi program, but they were by 1945, and this is what very few people really know much about. They were going in the right direction, but it was already too late. So, anyway, tomorrow night, by the way, the pizza, in theory, will show up around 6, and the show will start around 6:30, give or take whenever the pizza gets here.
Delta T, 30 minutes?
Yes, well, depends how far away from the campus the driver misses. You know, sometimes they've been in the fraternity houses, sometimes in the fine arts buildings. You know, they usually miss us by a wide margin. Though once they did come on time, so I can't say.
6, you said?
6 is the pizza, and 6:30 is the show. And that's got a big variability because the pizza guy never finds us. Okay, now, what then did happen? At the end of the war, it was rather important to get the German scientists away from the Soviet scientists, from the Soviets. And there was a mission called ALSOS, which was led by Samuel Goudsmit of the Goudsmit-Uhlenbeck spin work, who went throughout Europe and gathered up as many German scientists as they could and took them to England to Farm Hall, where they debriefed them and kept them away from the Soviets. And the nuclear scientists were there, and they were there when the Hiroshima and Nagasaki bombs were dropped, and it ended the hostilities. And we can argue about whether that was necessary. And I can tell you, I know people, my brother-in-law included, who were being shipped from the European theater to the Pacific at the time those bombs were dropped, and who owe their lives to the fact that the bombs ended the war, because they wouldn't be alive. There were so many casualties expected by having to fight a conventional war on the main island of Japan, that a whole lot of people lived because we didn't have to fight such a war. But there were things overheard, because the rooms at Farm Hall were bugged. The German scientists didn't know that. And first of all, their reaction was, it's impossible for the US scientists to have made nuclear weapons. After all, the great Heisenberg has shown that it would require using heavy water to moderate the reaction. Besides, weren't they, the Germans, the greatest scientists of all? They didn't realize that the greatest German scientists had left Germany when the Nazis came to power. Many of them were Jewish, many of them had Jewish ancestors, many of them couldn't stand the Nazis, and they just all got out. They were working for the Allies. So they were right. The German scientists had helped to create nuclear weapons. Not that that's the most thing that brings you the most pride, but that sentence is practically correct. And then they were going on to say, we German scientists were so moral and ethical that we were only working on heavy water concept to develop nuclear power plants in fuel-short Germany. And they didn't see the contradiction in this. Did anyone see the contradiction in that? You're going to build power plants in fuel-short Germany.
You could have just been burning the oil they were using in the tanks.
Yeah.
They could have just been using the oil from the tanks to burn it for fuel.
Exactly. If they had nuclear power plants, they wouldn't be so fuel short. Okay, so if they had built nuclear power plants, that fuel could be in their airplanes and their tanks and their trucks and whatever. So the idea that they were suggesting is an idea suggested by a group of unrepentant Nazi scientists as a cover story. Now, here's where it gets even more strange. Throughout his life after World War II, Heisenberg tries to claim that he had just been trying to lead the maniacs away from nuclear weaponry by his wrong calculations and his insistence on heavy water. He died in 1976 holding to this fairy tale. First of all, there's little to support this idea, and the Nazis would have killed such a deceiver because very rabid Nazi scientists like Stark would have turned him in. And I suspect Heisenberg was ashamed of himself and his colleagues and wanted to improve his place in history. And then there's a little known fact that I just mentioned a bit before. By 1945, the Nazis were converting a chemical plant at Oranienburg to produce enriched uranium, which says that they already knew what they had to do to make nuclear weapons. It just happens that the Allies found out about it and they bombed the living daylights out of the town of Oranienburg. I think it was in roughly this time of year, late March, early April, so that plant was destroyed. Of course, the war in Europe ended late April of 45. So it was already too late. They weren't going to get to making nuclear weapons, but they knew what they were going to do if they had time to do it. So, questions, comments? So tomorrow night when we see Copenhagen, you'll get a sense of the concern that Heisenberg had, and you're not sure what it was.
There's a fiction stories on network TV this last year called Manhattan. That's a historical fiction about what was going on in the Manhattan Project at Los Alamos. That's worth looking at if you have a chance to see it. It talks about a lot of the moral issues that people were struggling with, and particularly what happened when Germany surrendered, when the war in Europe was over. The big backwash of people that wanted to quit, and then of course there are people that wanted to deliberately share the results from the Manhattan Project with the Soviets as in their mind a way of preventing the next war, to make sure everybody had all the secrets.
it's interesting because by that time, the Soviets already did have the secrets. There were plenty of, at least 2 or 3 well-known spies working in the Manhattan.
Yeah, this is about.
Yeah, it's about them?
Yeah.
Oh,
yeah.
okay, okay. And by the way, everyone may say, oh, this is stupid and unnecessary, but the fact that both the Soviets and the United States had nuclear weapons, it's now, what, 70, almost 80 years with no major war. You know, there have been wars, there have been on local small scales, but you haven't had major engagements. We're all afraid. Not that anyone likes the idea, but we're all afraid. No one should have to live with that kind of fear. But anyway, at that time we didn't face the Nazis dropping nuclear weapons all over the world. Okay, so back to 1925. Heisenberg does not throw out correspondence, he modifies it, and he says, no, correspondence doesn't take classical into quantum. You put it in the basis of quantum mechanics, and you demand that it be one of the fundamental tenets of quantum mechanics. So that you take correspondence and you bring anything from quantum mechanics has to have something in classical physics that it corresponds to, not the other way around. And he insists that all that matters is what can be observed, and in this insistence he is part of a group of physicists, including Einstein and Schrödinger, that are strongly influenced by the philosophy of Ernst Mach, of the Mach number, you know, speed of sound and high air and all that. In fact, Heisenberg attributes to Einstein his concern with observables and nothing else, which again is one of those funny things because Einstein has this falling out with quantum mechanics over this business of what does it mean of what we can calculate. Anyway, Heisenberg analyzes Fourier components of time-dependent quantities, and he says in his paper, through a strange multiplication method, identifies these with such measurables as energy and dipole moment. The strange multiplication turns out to be matrix multiplication, but no one knows that yet. And we'll see that Ernst Pascual Jordan was the one to explain it to Born and then to Heisenberg. And for those of you who are interested, Ernst Pascual Jordan is German. His father happened to like things Spanish, so he gave him a Spanish middle name. And in science is known as Pascual Jordan, not Ernst Pascual Jordan. It turns out he is also, this is one of the German scientists who does become a member of the party, and as one of those who could easily have turned in Heisenberg. Anyway, the barrier, though, the lack of familiarity with matrices that prevented most physicists from taking to Heisenberg's model, and the widespread pleasure they took when Schrödinger comes out with a yet-to-be-published wave formulation. And we're going to see why. Matrix mathematics was not known to most physicists. It was only published when Heisenberg was 6 years old. And that book was published by M. Boucher in English in New York. It was a standard text for many years, and it was 1910 before it was translated into German, and it was only 1 year after Kovalevsky's treatise on determinants. So you get an idea that most physicists know nothing about, most physicists who are going to be looking at quantum mechanics, know anything about matrix theory. It certainly hasn't made its way into undergraduate education. It's probably barely into graduate education. And the second edition of Boucher's book made it into German in 1924, 1 year before Heisenberg publishes his strange multiplication. And this business of a matrix of quantities that does not have associative multiplication, you know, A times B does not equal B times A, that's weird. You know, people don't know about things like that until now. But Heisenberg certainly doesn't. He's doing his beautiful paper within a year of the book making its second edition in German, and only 15 years after the book first got into German. And surely he never took a course in matrix mathematics, because the math departments probably didn't even understand it. They were probably just coming to understand it. Now, there was a certain reluctance, of course, to teach something or to work in something that no one knew anything about. And consider that when Pauli was working with Born offered him a chance to work towards a logically consistent foundation of matrix mechanics, and Pauli and many others were reluctant to look at use matrices for theoretical problems. And Pauli, his refusal allowed him time to look at the statistics of electrons. I mentioned this before, and go on to the exclusion principle and the Nobel Prize. He was not alone. Heisenberg's paper was not reviewed in the Physikalische Berichte and the official abstracts of the German Physical Society. It was only given one sentence. Okay, this paper that wins a Nobel Prize, this paper that presents a way of calculating quantum mechanical stuff gets one sentence. And in the Physical Society of London, the Institute of Electrical Engineers, Common Science Abstracts, the American Physical Society probably don't even notice it, okay? Because nobody is familiar with it. Nobody can understand what this strange multiplication method is. And here's another neat piece of history. Emilio Segre, whose picture is here, speaks of his friend and colleague Enrico Fermi, saying that Fermi's attitude in 1926, when he left Born's group to go in Göttingen to go to Leiden, he says Heisenberg's great paper on matrix mechanics in 1925 did not appear sufficiently clear to Fermi, who reached a full understanding of quantum mechanics only later through Schrödinger's wave mechanics. So Segre goes on to say, I want to emphasize that this attitude of Fermi was certainly not due to the mathematical difficulties and novelty of matrix algebra. For Fermi, such difficulties were minor obstacles, but rather the physical ideas underlying this paper that were alien to him. That's making, lemonade out of lemons. I have a feeling that the mathematics were something so new to Fermi that he too would have to go study matrix mathematics before he could understand the math. Born had to search further for someone to put matrix mathematics on a firm footing. He couldn't get Pauli to work on it. Fermi was leaving to go to Leiden, and he was going to go to a conference, and somehow encountered Pascual Jordan while on a train trip. It's an interesting tidbit of history here. After the paper appeared, the meeting was going to be in Hanover. Born gets on the train, and he's talking with a colleague about Heisenberg's paper. Born shown here, and Jordan shown here. They're in the same compartment, and Jordan hears what's going on, and he has the temerity to speak to the professor as they get off the train. Now, this is unheard of in 1925 Germany. A student, basically, doesn't go up to a famous professor and say, Professor, I think I know what your problem is. I have some skill in mathematics, and I think what you're describing is matrix multiplication. In other words, Professor, you've got it all wrong. I can help you. I've got the math to do it. But Born is okay with that, and 60 days later, a paper comes out, the Born-Jordan paper, in which there are pertinent theorems of matrix math and the proof of this equation, which you all know and love, that PQ minus QP is equal to minus IH bar times the angular momentum operator. Wow, that's amazing. And this is also the first step towards the uncertainty principle. That the difference between these operators taken in different order depends on Planck's constant. This is quantum mechanics, and it's showing you something that is yet to be understood. Well, 2 months later, after they get together with Heisenberg, is on Quantum Mechanics 2, and it's a vast generalization of the 2 previous papers, Heisenberg's alone and the Born-Jordan paper, and they extend it to systems of many degrees of freedoms, canonical transformations, and quantum mechanical treatments of time-dependent and time-independent perturbations. So in essentially a period of, 3 months, from finding out what matrix multiplication is, Born pulls together with Heisenberg and Jordan the whole of matrix quantum mechanics. That's phenomenal. They don't have computers, they don't have calculators, they're doing all this on paper, just writing it down. And they get the right answers because it is correct theory. Heisenberg, however, from these analyses, he begins to realize that there are problems. Pairs of canonical variables are connected to Planck's constant in such a manner that you can't know both simultaneously with unlimited accuracy. You get these kind of problems. And this uncertainty principle is a fundamental feature of the quantum world. And since the whole universe, and now we're jumping ahead because we now understand that the whole universe was once very, very, very small. The delta x went to 0. The delta p was very large. Same thing, the delta t of the universe was once very, very small. So the delta E was huge. The amount of energy in the early universe was immense because the universe at the beginning had 0 time, a very, very small amount of time. So we're using uncertainty, a quantum mechanical issue, to understand a property of the universe when it was very young. It lets us reach back into the beginning of the universe, looking at a cosmological problem, just coming from that. So you get a sense that quantum mechanics governs everything. Okay, now, another conceptual development starts off this way. You start from light, not the mechanics of particle, because light is our main means of perceiving the universe. Light seems to be both wave and particle light, and it makes its choice depending on how we observe it. So as far back as Hamilton, efforts were made to understand the way light establishes the mechanics of light. And I say, remember Newton and his corpuscles of light. De Broglie had shown that things we thought of as particles could also be considered as wave. So now Schrödinger comes along and he follows a deliberate path, a mathematical path to a theory of wave mechanics. And his is a synthesis of wave-particle duality. Now let's talk a little bit about Erwin Schrödinger, because he's very different than Heisenberg. He's schooled in the classical gymnasium, which means he learns history, he learns philosophy, he learns Latin and Greek languages. As I say, he learns philosophy, he's very serious about it. It took him just 4 years, from 1906 to 1910, to receive his PhD from Fritz Hasernow in theoretical matters, Franz Exner in experimental work, and Wilhelm Wertinger in mathematics. It's quite a range of stuff in just 4 years. In 1911, Exner takes him on as an assistant doing experimental work. Very important point that you should keep in mind. Schrödinger becomes involved in the controversy between atomicity and continuous and the continuity of matter, and he comes down strongly on the side of atomicity. And you've got to understand, at the beginning of the 20th century, the argument was still pretty strong about was matter continuous or made up of atoms. And looking back at it from 100 years, you say that was nonsense. How could anyone think of matter being continuous? Well, they didn't have the information you've got. You know it better than they did, but at that time, there was an argument going on, matter might be continuous. The reason he comes down on atomicity is because he was influenced by Boltzmann. Boltzmann was his scientific hero. Along the way, he acquires a mastery of eigenvalue problems that is going to serve him well when he gets to solve the problems that he assigns himself. But understand that he's got a broad world view, much broader than Heisenberg's. Where Heisenberg sees the world from a Germanic culture point of view, Schrödinger sees the world on a much broader sense. He's looking at it from the point of view of the human race and humanity. He's more open to things. Maybe it's got to do with his being Austrian as compared to being German. It's not clear. But in any case, here he is, and he, from a philosophical point of view, is influenced by Spinoza, Schopenhauer, Mach, same old Mach with his only observable stuff matters. And like Einstein and Heisenberg and Schrödinger, he believes only what's important is what can be observed or measured. And it doesn't hurt that this theoretician knows the experimental aspects of physics. He actually works in that. His concern with observable is clear in his efforts to interpret the wave functions that come out of his wave approach to quantum mechanics. He's going to interpret it in terms of probability. And so our discussions of statistical events and stuff of last week become rather minor because all of quantum mechanics turns out to be a calculation of the likelihood of something happening. Okay, now let's move on here. Schrödinger, however, is a man who's never quite satisfied. In 1920, he's unhappy in Vienna, and he goes to work first with Max Wien in Jena. Then he takes an assistantship in Stuttgart. These are both engineering schools, and he's a physicist. So he's unhappy there, and he goes on to Breslau, and he finally settles at the University of Zurich in 1921 as a successor to Peter Debye. He of the Debye, the Debye conditions and states, whatever, when transitions take place. Anyway, we're going to talk about Debye and what Debye does to Schrödinger and how that makes Schrödinger do his work that leads to the Schrödinger wave equation in a moment. He stays in Zurich for 6 years, during which time he develops wave mechanics. He does phenomenally good work there, but he doesn't feel that he is recognized. So in 1927, he is recruited by the University of Berlin to succeed to the chair that Max Planck held, the most prestigious position in German science. Now he feels recognized and honored. 5 years later, the Nazis come to power. He is deeply repelled by them, and he gives up this position, and he leaves Germany, goes to the Institute for Advanced Study in Dublin, Ireland, stays there until 1956, when he returns to Vienna, where he dies just 2 years later. So he is clearly repelled by this, and he chooses to leave. As I said, most of the good scientists in Germany left. They did not stay to work with the Nazis. It turns out that Peter Debye identified Schrödinger as his replacement, and when he did it, it resulted in part from the fact that neither of them could understand de Broglie seminars. And so Debye has Schrödinger give some seminars about de Broglie stuff, and these seminars really impressed Debye. So from these seminars, Schrödinger can build. Schrödinger says these seminars were the starting point of his work on wave mechanics. Okay, here is Schrödinger. He's a middle development person. but he can get out from these seminars and get started on his work. And in fact, later he writes that he needed the pushing of Debye before he realized that the subject of wave mechanics would be of interest. So sometimes it helps to be pushed. Now, wave mechanics, like anything else, has a shaky start. Seminars gave rise to the effort to generalize these waves for bound particles, and he found a neat solution that gave rise to energy levels as eigenvalues of a certain operator. It turns out the Hamiltonian. And then he applies this concept to the hydrogen atom, and he finds out the results are wrong. It's very depressing. You know, and these guys who do this are easily depressed. So he applies this concept to hydrogen, gets the wrong results, and now we know that his error was not including spin. The spin energy is significant. You include it. If you don't include it, you fail. You get the wrong energies. You can't fault him because spin had not yet been discovered. All the energies were there, but not yet spin, and so when you compared his calculations to the data, it didn't work. He was so disappointed that he abandoned his method as inadequate. Okay? This is a theorist who does this beautiful theory, he's got results, it doesn't match the experiments, and he says, oh, it's a bunch of nonsense. Anyway, a few months later, he returns to his work, and he notices that if he treats the electron non-relativistically, he got agreement with observation in the non-relativistic limit. That is, for the transitions that are not relativistic. And he says, hey, that's not too bad. Maybe I have something here. And he gets together and publishes it in January 1926. That's just a few months after Heisenberg. And he publishes this complex diffusion equation, and he shows that a wave equation for a complex function, he sends it to Annales der Physik. The manuscript includes his results for the hydrogen atom. Then in the next 6 months, he submits all 4 parts of his wave mechanics, including time-independent and time-dependent Schrödinger equations, their solutions for the spherical hydrogen atom, and his comments on the meaning of the wave function and the calculations of measurable quantities. And the rest, as they say, is history. In other words, all of Schrödinger's wave mechanics is published in a 6-month period, just as all of Heisenberg's matrix stuff, together with Jordan and Born, is published in a 4-month period of time. Same period of time, roughly. So the scientific community, the physics community, goes with what they know. They know waves, they know wave equations, they know how to solve differential equations, even if it's got an I in it, which, by the way, means that it's also time reversal invariant. You know, so you change the sign of time, you change the sign of I, and the Schrödinger equation is still the same when you change the sign of time, which is nice, because so are all the other fundamental equations of science. Physicists immediately realized that they were familiar with Schrödinger's equation. Yet follow his math and his statistical interpretation of the meaning of the wave function fits with the non-causal concepts that first were put forward by Einstein. In other words, now Schrödinger is telling you that these may be the wave functions, but you multiply the wave function times the complex conjugate of the wave function, and you get the probability of the particle, if it's the positional wave function, the probability of the particle being in that place. And that probability will be high where you think it's supposed to be and low where you don't think it's supposed to be, but it could be there. Okay, the problem remains, however, do you define an acceptable wave function? And it's clear that by insisting measurables were all that mattered, only single-valued, finite, and continuous wave functions could exist wherever the potential energy was finite. Schrödinger actually writes all that stuff down in his papers, so go read them. I think they've been translated, so is Heisenberg's. I was teasing you about reading his paper. It's been translated. Yeah. There are philosophical difficulties. It's hard to accept that the most we can know about something is the probability that it happens. Okay, that's part of last week's discussion. Is that what we were saying? Maybe somehow something makes it happen. No, it's all we know is the probability that it happens. We don't know anything else. Nevertheless, it's beyond doubt that quantum mechanics works. It is the most precisely tested theory that we have. And it works exactly as advertised, to 8 decimal places. We've measured quantities based on this theory, and when we make the measurements, it works just the way it's supposed to. Exactly as predicted. Feynman and others have demonstrated that quantum concepts can remove singularities from other theories and make quantum phenomena essential to the foundations of physics. So the idea of quantum mechanics and quantum phenomena have become fundamental in our understanding of the universe, of our science. So in these 3 talks about quantum mechanics, I've tried to give you a sense of how this once unheard of subject was demanded by data and observation that we did not have. We couldn't explain. Line spectra of atoms, stable atoms, things didn't just disappear. Other such things that we could observe. We had to go through the exercise of trying to understand it. And finally, in this work of Heisenberg and Schrödinger, coming up with mathematical structure to handle the problems. It provides the most precisely tested science we've got. And it keeps on working. And by the 1950s, as I say, it becomes clear that it's a fundamental feature of the universe. Wherever you look, you see quantum phenomena. In the spectra of the stars, in the spectra of atoms here on the Earth, everywhere you look, there you see it. It's proven ever more exquisite experiments over the near half-century. And optics plays a critical role in this because it's how you probe, it's where you see data that demands quantum phenomena. We casually talk of energy levels, photon energies. There's the word photon. Didn't exist before we began to worry about quantum phenomena. Max Born, 1900. Transitions between stable states and the like, but it's rare that you look at the intellectual journey we took to get here. Today, quantum ideas have been used to explain quantum chromodynamics, which is where you're looking at the structure within protons and neutrons, where quarks are being held together by whatever it is, gluons or something like that. There's a whole lot of other stuff beyond what was done up to the 1930s. The point of going just that far is because that's when quantum mechanics had been established, and it was in place to provide the tools that are currently being used. And that's kind of where we stop on this part of the journey. So, have you got any questions about that? Comments?
You mentioned testing quantum mechanics to 8 decimal places. I'm recalling the lecture from Feynman on QED, talking about the double-slit experiment and the weirdness of it, particularly when you get down to single photons, etc. And he comments that, well, it's okay if you don't understand it, because you don't understand it either, but all you can say is that the physics used to describe this result has been tested to 18 decimal places.
Okay, I can't possibly argue with Feynman that it is 18.
14, I'm sorry, 14.
The reason I say 8 is that the fundamental constants are only given to 8. Planck's constant is given to 8. Electron charge is given to 8. Mass of the electron is given to 8. So I'll stick with 8. But if Feynman says 14, I won't argue with it.
It's the electron G factor.
Wait.
I was says the electron G factor is the one that's measured out to like 14 or 18 decimal places.
Okay, so what the electron G factor.
Yeah. Well, I can explain it if you
Yeah,
want.
please.
It's the constant that relates it's like basically like the coupling constant between the dipole moment and the spin operator. So it's basically like how much, or it's like the relative strength of the dipole moment based on the spin of the particle, more or less.
Okay, so at least one item is measured 14 decimal places, but until they extend Planck's constant by 6 more decimal places, I'm going to stick with 8. I mean, it is kind of curious. If you look at any of the standard tables and such, you just see them take extending.
As an undergraduate student, there was a room called the slave room in the physics building that was filled with tables, all the 8 decimal places. All these tables were calculated during the Great Depression in the U.S. when mathematicians were hired as part of the Work Progress Administration WPA program to calculate from series with mechanical calculators, trigonometric functions and so forth, out to 8 decimal places, and logarithms and so forth. So big volumes of looked at the book, and our students would go in and try to work problems using 8 decimal places, particularly calculating common orbits and that sort of stuff.
Nowadays, we have computers for doing things like that, and we still have students that put 3 decimal place data in and report 8 decimal place precision, which is insanity, and one gets marked down for doing that. So remember, never report a number more precise than your data. I had a major argument with the first student at USC over that. He learned it. Any other comments?